we'll select value, and oops, sorry, not value. We want to select intersect, and we're going to figure out where this horizontal line that we can't quite see right now because it's covering up the horizontal axis, where that intersects this parabola x squared minus 3. So we see that there are actually 2 points. Well, that means that if I have 2 points that are going to make this function 0, that means I'm going to have 2 asymptotes. And it's just as straightforward as that. That this guy will have a solution of x is approximately negative 1.7, and another solution of x is approximately, well, now we have to calculate the other one, so I'm going to do an intersect, and that'll be this point over here, and that's going to be at about 1.7. So at negative 1.7 and positive 1.7, I'm going to have asymptotes. And these are of the form x equals, since that's the value that will make the denominator undefined, and x equals. And now it's, well, there are really 3 regions if you think about it. There's the region to the left of this asymptote, the region in between these 2 asymptotes, and then the region outside of that asymptote. Well, it's going to be somewhat difficult to exactly know what's going on, so let's just graph it, and let's take a look at the function as a whole, now that we know exactly where the asymptotes are. So we're going to plug in 2x plus 4 divided by x squared minus 3. Make sure we put those in parentheses. And we graph that, so I'm going to just set my zoom to standard since I know where all the behavior is taking place. And here's kind of what I get. Now, it's really hard to see, so, I mean, other than the fact you can kind of see that we've got a function going up this way, similar to what we've seen in previous graphs. And it kind of looks like it almost does an L, but that's just because we have this, that our graph is kind of, you know, outdated in the graphical sense. And so we get something that looks kind of goofier than we would want it to look. Actually, let me zoom back out and go back to my zoom standard. So I see that as you get closer to that asymptote, we have a function that approaches approaches as x approaches that value, y goes up. And similarly, even though this kind of looks like an N, it's more of a U shape, and it kind of looks like this. And then within here, same type of deal, we have an asymptote that approaches along this way. Now, what is the use of this? Well, there isn't really much use for the impractical values. Like, for example, the negatives, we probably in a real-world scenario wouldn't be using these. And we may not even be using the stuff that's happening here, but at least definitely, in most practical settings, we would only be looking at positive values of x. So what we're just getting at here is thinking about and seeing what the graphs would look like. Now, there are rules for it that you could probably memorize, but I think it's much more interesting and conceptual if we can just figure out where these horizontal vertical asymptotes are, and then figure out what we need to figure out. So next we'll look at a real-world example. Now you might choose to pause and read through this right now so you know exactly what's going on. We're modeling Exxon Valdez, the oil spill, and the cost to clean it up, depending on what percentage P you want to clean up. So as you might imagine, we would probably expect that the bigger percentage of the spill you want to clean up, that will result in an output that has a higher cost. And we don't have to have this in function notation if this makes it easier to see. And in fact, if you just remember that cost is y and the percentage is x, then you can use x and y if that makes it more comfortable. So we want to create a table that provides the cost to clean up. P equals 10, 30, 50, 70, 90. It's basically, as we get closer to 100%, let's just see what's happening. So I'm going to plug this in. I'm going to do my 0.08x, divide that by 100 minus x. And what I'm going to do is just set my table value to start at 0% and go up by tens. Now notice that this is, you don't have to convert it to decimals because the input of the function is the percentage value. And now if we look at the table, we start to observe to see what's happening. Now this is in billions of dollars. So we see that as you want to clean up more and more, suddenly there's this explosion of cost. That the costs seem pretty stable, they're not increasing by too much. But then once you start hitting 70%, 70 to 80, it almost doubles, and 80 to 90, it more